In this lecture, we're going to talk about Mohr's circle of strain. Now, we're already familiar with Mohr's circle of stress, so that'll make things a lot easier for us. We have our plane strain transformation equations that I've written down here. I won't read through them again, but I do want to note, as we pointed out when we derived these, that they are very similar to the stress transformation equations, except instead of sigma x, we got epsilon x. Instead of sigma y, we have epsilon y. Instead of tau xy, we have, now this is important, gamma xy divided by 2. So we have a divide by 2 that shows up on our shearing strain terms. So without getting into the details, we can construct our Mohr's circle of strain based on the fact that we can write these in a slightly different way. There we go. That instead of epsilon x prime, we can make that epsilon n. Instead of gamma x prime y prime, we can say that's equal to gamma nt. And then we can write this as epsilon n minus epsilon average quantity squared plus gamma nt over 2 quantity squared is equal to a constant squared. We do this by squaring and adding the epsilon x prime and epsilon and the gamma x prime y prime equation. Again, go back and review the Mohr's circle for stress lecture to get into all the details. So to construct our Mohr's circle of strain, it's very similar then to what we do for stress. For a given strain state, and I'll show this on a square just like I do for stress, just to make things look more similar. We would know epsilon x, epsilon y, and gamma xy. And we may either want to find the principal strains, the maximum shearing strain, or we can find a new state of strain off at an angle using Mohr's circle. But we want to construct an axis for our Mohr's circle. Instead of the sigma axis, we have an epsilon axis. Instead of positive tau being down, we're going to have positive gamma over 2 be down. And we're going to plot 3 points. Our x point is going to be epsilon x, comma gamma xy divided by 2. Our y point will be epsilon y, comma minus gamma xy divided by 2. And the center of our circle is going to be epsilon average, comma 0, where epsilon average is equal to the average of the in-plane extensional strains epsilon x plus epsilon y over 2. So maybe this particular circle plots like this. There's the center. Maybe this is the x point here. And I'm going to cheat this a little bit. Maybe the y point ends up here. And then we can have a circle that connects those two endpoints along that diameter. It's a pretty sad looking circle, but you get the idea. The points right here are the farthest we can get along the strain axis, and those are our principal strains. Epsilon P1 and 2 are the average plus and minus the radius. Okay, the way that we can find the radius is by dropping a perpendicular line down. Knowing this distance is the gamma over 2 distance, and knowing this distance right here, which would be epsilon x minus epsilon average. Epsilon x would be the distance from the origin to this point. Epsilon average would be the distance from the origin to the center of the circle. And so our r squared would be equal to d squared plus that h squared. So we can find our radius that way. If we want to find our maximum in-plane shearing strain, we can drop a vertical line through the center. Down on the bottom, this would be the point epsilon average, comma gamma max in plane divided by 2. And up at the top, this would be epsilon average, comma, gamma maximum in plane divided by 2, but with a negative sign associated with it. So the maximum in plane shearing strain divided by 2 would be the radius of this, what I'm going to call my 2D circle. And this would be my 2D radius that I calculate right here. So the gamma maximum in plane would be twice the radius or the diameter of that Mohrs circle. If we want to account for generalized plane strain, in generalized plane strain we may have a non-zero epsilon z. If epsilon z is not 0, or even if it is 0, if gamma x z, gamma y z are equal to 0, then epsilon z is a principal strain. And I'll call that my third principal strain. If we want to construct a 3D Mohrs circle of strain, then we would plot epsilon p3 comma 0. Wherever it lands is where it lands. It could end up over here to the right of epsilon p1. It could land in between 1 and 2, or it could land over here to the left of 3. Just for somewhere to draw it, I'm going to draw it out here. So that's epsilon p3 comma 0, which is epsilon z comma 0. And then to construct the 3D Mohrs circle, we draw circles, 2 additional circles that connect all the principal strains with one another. If we wanted to find the absolute maximum shearing strain, well, divided by 2, that would be equal to the maximum radius of all of our Mohrs circles. In this case, it would be epsilon p1 minus epsilon p2 over 2, p3 over 2 would be the radius of the biggest circle. So gamma maximum absolute would be equal to 2 times my biggest radius. Alright, so the other thing that I need to point out before I leave this page is that the angle of rotation, just like for Mohrs circle, is twice the angle if we want the in the material. So on the Mohrs circle, the angle there to the principal stress direction is 2 theta p. I can calculate the tangent of 2 theta p. It would be equal to the height divided by that distance d. If I solve for the angle theta p, that's the angle in the actual material. A way to remember that is if you notice that epsilon x and epsilon y are 90 degrees apart, but here on the circle those points are represented by 180 degrees apart. Every angle of rotation of the material corresponds to twice as much that angle in the Mohrs circle. So if I wanted to show the principal stress state, the principal strain state, in this particular problem it would look like this, where the x point would rotate to epsilon p1 and the y point would rotate to epsilon p2. 45 degrees from that, I would have my maximum in-plane shearing strain state with epsilon average all the way around. And in this case, I would have a positive shearing strain for my in-plane maximum, which I'm going to write here, gamma max in plane. Right. So that's went through that real quick, but we have a lot of experience with Mohrs circle already. Again, everything is the same except for that gamma over 2 that shows up in each one of these terms. Let's do an example, and I think we'll see how this Mohrs circle works. Okay, so let's take a look at this example. In this example, we have a 0, 45, 90 degree strain gauge rosette that's been attached or adhered to the surface of a component, and that component's in a state of plane stress, meaning that sigma z is equal to 0. I put the x and the y axis in the plane of the material. This rosette has 3 strain gauges, the A, the B, and the C gauge, and the readings are as follows: 220 microstrain, 170 microstrain, and minus 60 microstrain, respectively, for the A, B, and C gauge reading. This is a linear elastic material with modulus of elasticity of 210 gigapascals, and Poisson's ratio of 0.3. That would be for steel. And we want to find the principal stresses and the principal strains at this particular location. It's a very sophisticated problem, but it's a very practical problem. I had to do this kind of calculation routinely when I worked at General Motors. So the first thing we need to do is to figure out what our coordinate strains are. Now, we know because of the 0, 45, 90 degree strain gauge rosette that the X direction strain gauge reading will be the same as the A, and that's going to be 220 microstrain. The Y strain is the same as the C gauge reading, and that's minus 60 microstrain. And the shearing strain gamma XY at that location is 2 times the middle gauge minus the other 2, which would be equal to 2 times 170 microstrain minus 220, and a minus and a negative give a plus 60. And those are microstrain units. So let's see what we get for gamma XY. Let's see. 2 times 170 can take away 220, and we're going to add 60. I got 180 microstrain. Now there's 2 ways that we can approach this problem. One way is that we can use Hooke's law to convert these strains into stresses right now, and then do a Mohrs circle of stress. Since we just talked about Mohrs circle of strain, however, let's use a Mohrs circle of strain for this problem. So we're going to end up wanting to plot 3 points. Let's label them here. We'll draw the circle on the next page. The X point is epsilon X comma gamma XY over 2. That's going to be 220 comma 90 in units of microstrain. The Y is epsilon Y minus gamma XY over 2. That's going to be equal to minus 60 comma minus 90. And the center of the circle is epsilon average comma 0, and the average is going to be 220 plus a negative 60 divided by 2. Let's see what we get for that. That's 80 microstrain. So the center of our circle is going to be 80 comma 0. Let's go ahead and plot those points up. Alright, so there's my coordinate axes there. First thing I'm going to plot the X point. So I go over 220 and I go positive direction 90. And remember, positive is downward for our Mohrs circle. And I want to label this as the X point so I keep it straight. Center of the circle is at 80 comma 0. Maybe it's about here. And my Y point is at minus 60 minus 90, so maybe that puts me about here. I draw a straight line that connects those points, and then a circle so that that line is the diameter of a circle. Alright, so if I want the principal strains, I know that the principal strains are located here and here. Epsilon P1 and 2 is the average plus and minus the radius. I need to find the radius. I'm going to drop a vertical line down to this point right here, and this height is 90, and this distance is going to be 220 minus 80. Okay, so that's 140. So R squared is equal to 90 squared plus 140 squared, just by using the Pythagorean theorem. And I solve for R, and I got 166.4 microstrain. So epsilon P1 is the average plus this radius term. Epsilon P2 is the average minus this radius term. And again, those are in units of microstrain. So I get 246 microstrain and minus 86.4 microstrain. That's this location right here. So there's epsilon P2 comma 0, epsilon P3 comma 0. Epsilon P2 comma 0, and over here epsilon P1 comma 0. Now there is a third principal strain, and it is probably not equal to 0. So we're going to need to figure out what that third principal strain is. But in order to do that, we're going to have to find the stresses first. Okay, so now we're going to find our principal stresses. So we know from Hooke's law that we can write down that the strains are related to stresses. In terms of principal stresses and strains, epsilon P1 is equal to sigma P1 over E minus nu sigma P2 over E minus nu sigma P3 over E. And I'm going to go ahead and write down the other two equations, and basically all I'm doing is cycling through the subscripts. And I know the material properties E and nu. So now I have found the values for the left-hand side in this equation. Now I know sigma z is equal to 0, and it said it was in a state of plane stress. So sigma z is the third principal stress, and it's equal to 0. So that goes away in this equation and in that equation. What I have now then is two equations and two unknowns. I'm going to do a little bit of algebra to solve for the stresses in terms of the strains. Let's come over here and do that. First thing I'm going to do is I'm going to multiply both sides of both equations by the modulus of elasticity E. And I want to eliminate one of these terms. If I multiply the bottom equation by Poisson's ratio and add them together, then on the left-hand side, I have E epsilon P1 plus nu E epsilon P2, and I have sigma P1. The sigma P2 term goes away, and I have minus nu squared sigma P1. If I solve for sigma P1, that's going to be equal to E times epsilon P1 plus nu epsilon P2 divided by 1 minus nu squared. Now if I were to repeat this process but solve for the other term, since there's some symmetry in these equations, sigma P2 would be equal to E the epsilon P2 plus nu epsilon P1 divided by 1 minus nu squared. So now we have some equations and we can find those stresses. Let's do that on the next page. Alright, so I'm substituting in the material properties. I've written down one of the equations already. Let's go ahead and talk through the second equation. Sigma P2 would be equal to the modulus of elasticity. Now it was 210 gigapascals, so that's 10 to the 9th pascals. The epsilon P2 minus 86.4 minus, plus nu, should be a plus right there, plus nu times epsilon P1, which is 246 microstrain. And so microstrain is units of 10 to the minus 6. And then it's going to be divided by 1 minus nu squared. So let's see what we get for this calculation. Okay, so for the first one, I got 50.79 or 50.8 megapascals. And let's do the next calculation. 210 gigapascals. Then I have negative 86.4 plus 0.3 times 246. And I need to account for my microstrain units, and then divide that by 1 minus 0.3 squared. And I got a pretty small number this time. I got minus 2.91. Okay, so these are the principal stresses, and the reason why they're the principal stresses is I use the principal strains in order to calculate them. Now, we already talked about how sigma P3 was equal to 0. There can be a strain in the 3 direction, so we need to calculate it. Epsilon P3 is equal to sigma P3 over E minus nu, sigma P1 over E minus nu sigma P2 over E. Sigma P3 being 0, we have minus 0.3 times 50.8 megapascals minus 0.3 times a negative 2.91 megapascals, and both of those terms are divided by the modulus of elasticity, 210 times 10 to the 9th. So let's see what we get for the strain in the 3 direction. Okay, and I got minus 68.4. Let's see, I need to be careful here. Since those are in megapascals, I need to take this times 10 to the 6. I got minus 68.4 microstrain. So now we have all of our principal strains and all of our principal stresses for this particular problem, which is what they were asking for. Again, a fairly sophisticated problem. This is the kind of problem that I could put on a final exam, because it really brings a lot of things together into one problem. There's more than one approach you can take to this problem as well. But it's a nice problem because it uses Mohrs circle of either stress or strain, and it requires an understanding of 3D Hooke's law and what principal stress and principal strain states really are. Alright, so that's it for this lecture. Please watch some of the other integrity videos for specific examples of homework problems out of your book.